Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for December 5th, 2012.
On today's biophotonics themed show, a fiber optic wrench twists and turns tiny particles, near-infrared imaging gets a big boost, an X-ray laser helps fight sleeping sickness, and implantable silk micromirrors enhance imaging.
A tiny virtual wrench created from laser beams emitted at the ends of a pair of optical fibers can precisely twist and turn microscale objects in any direction and along any axis without moving an optical component, an ability that sets it apart from other optical tools. Developed at the University of Texas at Arlington, the fiber optic spanner, which is the British word for wrench, is more controllable and versatile than optical tweezers currently used for biomedical and microfluidic research, especially when it comes to working deep inside the body. This new twist on controlling the incredibly small will allow single cells to be manipulated for cancer research. In tests, human smooth muscle cells were rotated and shifted without damaging them, demonstrating that the technique could have both clinical and laboratory use. Other possible applications include mixing or pumping the fluids in lab-on-a-chip devices, or helping to stretch and uncoil a DNA strand, allowing it to be more efficiently sequenced. The researchers also envision applications in the direct conversion of solar energy to mechanical energy. The findings were reported in Optic's letters.
Studying arterial diseases and therapies just got easier thanks to a new fluorescence imaging technique that allows researchers to visualize the blood flow of living animals with unprecedented clarity. The Stanford University technique called near-infrared-II imaging, or NIR-II, involves shining a laser over a living subject, in this case a mouse, after water-soluble carbon nanotubes have been injected into its bloodstream. The near-infrared light causes the specially designed nanotubes to fluoresce at a longer wavelength of 1 to 1.4 microns, which is then detected to determine the blood vessel's structure. The substantially longer wavelength scatters less and is the key to the sharp, finely detailed images. The method also yields a fast image acquisition rate, allowing blood flow to be measured in near real time, a feat previously not possible. The technique will help better study arterial blockages and constrictions that cause, among other things, strokes and heart attacks. Because NIR-II can only penetrate a centimeter into the body at most, it won't replace other imaging methods, but it will be powerful enough to study animal models by replacing or complementing X-ray, CT, MRI, and laser Doppler techniques. The study appeared in Nature Medicine.
The detailed structure of an important protein involved in the transmission of African sleeping sickness has been mapped using an X-ray laser. It's an important step towards developing a new drug to treat the fly-borne illness and the first new biological structure solved with a free electron laser. An international group used the SLAC National Accelerator Laboratory's LINAC coherent light source to study a disease transmitted by tsetse flies that kills an estimated 30,000 people each year, and about 60 million people across Africa are at risk for contracting the disease. The increasingly drug-resistant parasite's artillery includes an enzyme that breaks down the protein of its victims. Scientists hope to stop the disease by mimicking a natural inhibitor that keeps this enzyme in check until the parasite invades the victim's bloodstream. However, the enzyme is so similar to one in humans that blocking it could be harmful to the patient. To design a drug that attacks only the parasite, researchers needed more detailed information about its structure. Typically, researchers determine these protein structures by shining an X-ray beam onto a protein crystal, but it's difficult to grow crystals large enough to withstand this radiation for long enough to capture the necessary information. A new method, known as serial femtosecond crystallography, overcomes the radiation damage problem by using short X-ray pulses that radiate a steady stream of small crystals. These pulses are so fast that a snapshot of information can be recorded before each crystal is destroyed. The results were published in Science Express.
In a follow-up to a story we brought you a few weeks ago on silk-based optics, a new study says a silk-based implantable mirror can significantly enhance tissue imaging and simultaneously enable photothermal therapy, monitor drug delivery, and administer drugs. The biodegradable and biocompatible devices, developed by Fiorenzo Omenetto of Tufts University, dissolve harmlessly at predetermined rates so they don't have to be surgically removed. Omenetto says the work showcases silk's potential to go beyond imaging and serve multiple biomedical functions. The mirrors were created by pouring purified silk protein into molds in the shape of multiple micro-sized reflectors and then air-dried. When implanted in tissue and illuminated, the silk mirrors cause more light to be reflected from within the tissue, enhancing imaging. When implanted, these MPAs reflected back photons that ordinarily are lost with reflection-based imaging technologies, enhancing imaging even in deep tissue. The researchers also demonstrated the silk mirror's potential for administering therapeutic treatments by mixing gold nanoparticles into the solution before casting the MPAs and also embedding them with a cancer-fighting drug. When exposed to enzymes in vitro, the drug was released as the mirror gradually dissolved. The amount of reflected light decreased as the mirror degraded, allowing the researchers to accurately assess the drug delivery rate. The technology was described in the Proceedings of the National Academy of Sciences.
And you can hear more about his work from Dr. Omanetto himself in a recent interview he did with Light Matters. You can click on the link in this video or access it at photonics.com/lmsilk.
Well, that's it for this edition of Light Matters, Photonics Media's weekly newscast. We'd like to hear from you. Tell us what you like or don't like about our program. We welcome your comments and suggestions at lightmatters@photonics.com.
You'll find links to share and subscribe to Light Matters by clicking the Share with Friends button on our video player.
Thanks for watching, and we'll see you next week.